Mass action law. This is one of the most important topics which you have studied till now. Mass action law provides a relation between free electron concentration and hole concentration of extrinsic semiconductor with intrinsic semiconductor kept at the same temperature. Suppose we have extrinsic semiconductor and intrinsic semiconductor. Both are kept at same temperature T. For the extrinsic semiconductor, we assume the free electron concentration to be N0 and hole concentration to be P0. Similarly, the free electron concentration in intrinsic semiconductor is Ni and hole concentration is Pi. But since it is an intrinsic semiconductor, free electron concentration will be equal to hole concentration, making Ni equal to Pi. In the last lecture, we studied that the generation rate is actually function of temperature. We have assumed that the function is f1t. Similarly, the combination rate is equal to alpha multiplied by free electron concentration multiplied by hole concentration. Also, alpha is actually another function f2 of temperature. Now for equilibrium semiconductor, we know that generation rate is actually equal to recombination rate, irrespective of whether the semiconductor is extrinsic or intrinsic. For extrinsic semiconductor, we put the value of generation rate and recombination rate. We can write N0 into P0 is equal to function f1 divided by function f2, and both the functions f1 and f2 are functions of temperature. Similarly, for intrinsic semiconductor, we can write Ni into Pi equal to function f1 divided by function f2. Since Ni is equal to Pi, we can also write Ni square equal to function f1 divided by f2. Now, for the same temperature, we can equate the value of function f1 divided by function f2 from the different cases of extrinsic and intrinsic semiconductor, which will give us the equation N0 into P0 is equal to Ni square. And this particular formula is called as mass action law. This is very important. You can also find this formula in other forms like Ni plus delta N multiplied by Pi plus delta P equal to Ni square. This delta N and delta P are the change in free electron and hole concentration with respect to intrinsic carrier concentration. However, we can simply say that for n-type extrinsic semiconductor, delta N is positive, whereas delta P is negative. Also, for extrinsic semiconductor, Ni plus delta N is equal to N0, which is free electron concentration in extrinsic semiconductor. Similarly, Pi plus delta P is equal to P0, which is hole concentration in extrinsic semiconductor. Now we assume that doping concentration Nd is significantly greater than Ni and the semiconductor is kept at a temperature T such that ionization efficiency of donor electrons is nearly 100%. Since Nd is significantly greater than Ni, we can write Ni plus delta N to be nearly equal to doping concentration. This delta N is the number of electrons which arises due to the doping concentration. Now we can write doping concentration Nd into hole concentration P0 is equal to square of intrinsic carrier concentration, giving us P0 equal to Ni square divided by Nd. We also know that for an n-type semiconductor, P0, which is the hole concentration, is actually the minority carrier, giving us the minority carrier concentration is equal to square of intrinsic carrier concentration divided by doping concentration. For an extrinsic semiconductor, majority carriers are the carriers which are present in abundance or whose value is greater than intrinsic carrier concentration. So, for n-type semiconductor, N0 is the majority carrier. Similarly, minority carrier is the carrier whose concentration is less than intrinsic carrier concentration. Therefore, for n-type semiconductor, the minority carriers is P0. I hope you understood the derivation of this particular formula through which we can find the minority carrier concentration in an extrinsic semiconductor if intrinsic carrier concentration and doping concentration is provided. The analysis which we have done for n-type semiconductor can also be done for p-type semiconductor. One more important point you have to remember that mass action law is valid only for non-degenerate semiconductors. This formula is not valid for degenerate semiconductors. We will conclude the lecture by providing the definition of mass action law. Mass action law provides a relation between free electron concentration and hole concentration of extrinsic semiconductors with intrinsic carrier concentration when both are kept at same temperature.